everyone. I am Hy Tran. I am a master's student in his last semester, and today I will be showcasing some of my fault identification work and machine learning work as it pertains to the Illinois Basin, an area of carbon capture, storage, and utilization. Going over our motivation, this is our so what, why do we do the things we do. Next, we'll be going our background, what is the context, what sort of data we are going to use. Next is our workflow. After that will be results of discussion, combining that to sort of streamline this talk, and finally key takeaways or conclusions. Well, fault risking is a critical part of many subsurface projects, from traditional well planning and operations to new venture projects such as geothermal. In our case, carbon is injected into the Mount Simon Reservoir, right here, which is comprised of fluvial fine to coarse arcosic sandstone and conglomerates, where the outclare overlaying it acts as a mudstone baffle, which is a seal, which prevents the further migration of CO2. So about 3 months after injection into the Mount Simon Reservoir, there's reactivation in the basement. So microseismic readings were recorded in the granitic rhyolitic basement right here, which indicates there's some sort of reactivation happening. Knowing where these faults are means preventing and avoiding problems like reactivation, so earthquakes, but more likely than not means avoiding CO2 leakage into the air and water. Avoiding these issues means therefore preventing public outcry of new technologies and therefore more governmental and public support. This is especially important when your industry is heavily reliant on the public or governmental support. In the Illinois Basin, the EPA and the local government's major concern is the potential of surface and groundwater contamination of CO2. So the largest nearby aquifer is the Mahomet Aquifer in this sort of dash gray area right here. This aquifer provides over 840,000 people with water, and that population is growing. So just to break down a couple of these figures, this is the CO2 plume from the Illinois Industrial Carbon Capture Storage. Illinois Industrial Capture and Storage 2020, and I have that plume recognized right here just to show sort of the extent of it, as well as a 5-mile radius circle focused on CCS2 and CCS1 respectively. The Mahomet Aquifer should be around this region right here. It's about 5 miles away from the closest CCS2, so there is potential risk. I like this quote a lot, but I'm not sure who it's by. It's something I read and it stuck with me. Science exists to either confirm or reject ideas based on evidence. So we take our pre-existing ideas and we build upon it. For example, my work is based on the previous works by Diana Salazar. So studying the Illinois Basin can help us understand other areas of interest, so highly applicable, so not just for CCUS, but traditional well planning and operations, so avoiding problems such as mud loss and drilling large portions out of the lateral are extremely important, and fault analysis and risk are important to geothermal as well. For data, we have two data sources, microseismic, more on this later, and reprocessed high resolution post-stack migration. So this data was acquired in 2015 and reprocessed in 2019 and has a sample rate of 2 milliseconds, record length of 4 seconds, and a bin size of 5 by 40, which is kind of crazy. With seismic reprocessing comes a basement estimate of around 6,300 to 6,700 feet. For the sake of our project, we select 6,500 because it is between the upper and lower calculations. Moreover, we will use depth slices and not horizon slices. In my previous works, I found that depth for time slices as compared to horizon slices results in sharper fault features. So we stick to 6,500 depth as well. The microseismic data, so they are collected in 3 downhole sensors. In each CCS. So for example, CCS1 is collected in CCS1, GM1, and BW1. For CCS2, they are collected in CCS2, GM2, and BW2. BW is verification mode, GM is monitoring well and CCS injection. They're also collected in 5 subsurface sensors installed by the Illinois State Geological Survey, so it's definitely orange, and clusters were reported about 2 months after injection into CCS1. Why we care? Well, traditional seismic actions effectively decrease fault uncertainty in the upper basement. Can machine learning be used to improve the mapping of these little basement faults? Can seismic attributes of machine learning detect faults with a microseismic history? Will these methods decrease the uncertainty of mapping in the basement? So first, we start with our seismic data, there's a microseismicity, locate area of interest, and crop it down to save computational time. And we add a structural filter, more on this later. And then from that structural filter, we're able to calculate our geometric attributes. So appearance, curvature, and geometry respectively. Geometric attributes are the old or gold methods. They provide the foundation for what we'll do later on. After we compare and contrast our seismic or geometric attributes, we can apply machine learning. Then finally we evaluate the current observed and adjust parameters and it loops because science, we can always improve our results. These are the ones that we'll be focusing on our presentation, so anything that we read, I do have GTM and GLTM, but I'll be focusing on this for now. And the other seismic attributes, especially because we're using high resolution seismic data. Once these high resolution moves are removed to the basement, we use moreover, our basement also pigments. So it's going to be really noisy. So a preconditioning steps of the structural filter is crucial. So I'm going to look at this. So this is before SOF and after SOF. As you can see, it sharpens these faults or limits really nicely. And the offset is a lot more clear. Helps with interpretation, really nice. But another thing we should look at is the noise. Are we comfortable with removing all this horizontal stuff? Are we comfortable with removing all the vertical stuff? That's the important part. You can also analyze the noise itself, so you're not really missing anything. Yeah. That's why I felt comfortable. Classic similarity attributes, which measure the similarity of neighboring traces in inline cross-hand direction. So these help with like large-scale faults or faults with a really clear offset. Whereas curvatures are used to map subtle seismic faults through reflecting off this fault. And aberrancy if K1 and K2 are the anticline syncline or the fold respectively, the aberrancy would measure between. Again, really good for faults with road flow. Another thing to know, we also look at entropy and chaos. So disclosure, so faults tend to have correlated with higher dispersion. When we test this out, we utilize a pre-built model. And the reason why you use a pre-built model is we're trying to enhance faults that are not easily detectable. So it makes sense to use a pre-built model. GTM is a nonlinear reduction technique that finds pattern between data points, so it finds a relationship between varying attributes, and that's it. SLM is pretty similar, but because on previous studies by Daniel Salva, GTM seemed to perform better, so we tested GTM anyway. PNN is better for shallower depth, where faults can be clearly mapped or focused in the basement, so it seems counterproductive to build with PNN. So we applied SLM, and now we run covariance on that aspect output. This is what we get. So we're looking at FR1, FR2, FR3, and mainly focusing on FR1. But you can see this nice linear here too. It lines up really nicely with this Microsoft data that we required. And here you can also see that there's some sort of lineaments in this area as well as here. But the clearest limit is in FR1. So fall enhancement is extension of coherence because it requires a previously calculated coherence volume from its output. Um, well, skeletonization calculation and further linear detected. So that's why I did it. See if I can sharpen the points apart there. Excuse me. Ideally, these post-coherence steps should improve by time section. In the case of our study, it really improved that drastically, but it does retain that limit that we saw in FR1, as well as some sort of limits in the other regions as well. Getting into curvature sweep, so again, see if the earlier, and then co-render K1 and K2. What's important about these regions that you could potentially see some sort of remnants in this area, but that could be due to bias, as we saw in the already. But an important part is that curvature and variancy bring out areas that coherence is there, but it's not. So areas like this region where we don't have microseismicity. There is some sort of movements caused by this yellow dash pattern. But in terms of our FR regions, the limits are that. But there is definitely something that are variancing curvature at the point out. So what does the arbitrary line look like? So we're cutting a line from R1, seeing if there's some sort of fault there, and we do see that nice offset right here, or discontinuity of reflectors. And when we look at overlay microseismic output with a projection of 220 feet, you see that the microseismic really clusters around that offset which is pretty awesome. And then CNN, so actually when I first saw this, I was having a reaction. I was having a good time. The sky was good, everything was nice. But just to break down what I'm seeing, so let's start with the color bar. So the color bar, I adjusted it a bit. And the default color bar is black to white grayscale. But for this case, I set 50% to be a rainbow. Anything above 50% is a rainbow, with red being 100% fault probability. And then the same thing, cut that area, look at an arbitrary line, overlay microseismic, and this is what you see, the arbitrary line, and this is what the microseismic overlap looks like. And it's really, really nice because it does cluster around CNN, sort of areas of fault probability, and here is the offset right here, which is really nice. Another thing to break down is the meaning of these colors in this microseismic. So from 2011 to 2015, that was the first wave of injection, and 2015 to 2018, the second injection. So these white correspond to the first wave, and the rainbow corresponds with this, which is pretty cool. And then finally, prepping everything up, most traditional seismic attributes of temperature decrease fault resiliency and basement cell can machine learning be used to improve mapping effects? Yes. Can seismic attributes of machine learning detect faults in microseismic history? Yes. You see the open in the previous slides. Will these methods decrease the uncertainty of mapping from basements? And just key takeaways, attributes of machine learning, so geometric attributes of machine learning, so it's about elements, minus data, we saw, highly applicable to other areas of interest, and it's not that hard yet, but it can be. So we have to continue to do this and mitigate uncertainty and make the best. Thank you. Real for enjoying the research group. Thank you, Dr. Marcus, for providing such a strong foundation and asking Dr. Lugo, expertise how to do a legal and how that's very helping me with my perspective data, of course, like ASCII, great research group as a whole, so kind of software data, and thanks on the data and the data in the Illinois Basin, and as a sponsor. Thank you for coming, and